Hi, my name is Paraskevi Nusi, and I am a postdoctoral researcher at Aristotle University of Thessaloniki. In this session, I will present a work entitled Improving Electric Load Demand Forecasting with anchor-based forecasting method. This work was conducted in collaboration with Dr. Maria Gelepi and Professor Anastasios Stefas in the context of Maleno project. The presentation includes a brief introduction of the electric load demand forecasting task and the description of the proposed method, followed by the experimental evaluation. Electric load demand forecasting describes the task of predicting the electricity demand by employing historical load data. In this work, we deal with a short-term forecasting case that is the one-day-ahead forecasting task on an hourly basis. In particular, we deal with the Greek energy market. Electric load demand forecasting is a challenging problem in the energy markets due to the variety of factors affecting the forecasting performance, associated with many critical applications ranging from power system operation and planning to energy trading. Earlier works for addressing the electric load demand forecasting task include statistical and machine learning models. Subsequently, motivated by the exceptional accomplishments of deep learning models in a wide variety of problems, they have recently been proposed in order to address this task too, accomplishing remarkable performance. So moving on to the proposed method. The proposed method draws inspiration from the anchor-based object detection methods. In these methods, the goal is to predict the bounding boxes of objects of interest. Hence, the network is provided with predefined boxes, or anchors, and the target is formulated as prediction of offsets. That is, instead of predicting the absolute coordinates of the bounding box, the network predicts the offset, simplifying in this way the task and thus making it easier for the network to learn. Thus, drawing the analogy from anchor-based object detection, we argue that considering the ELDF task, we can define an anchor and transform the problem into predicting the offset instead of predicting the actual load value. Specifically considering the one-day-ahead load demand forecasting task, we use as anchor the electric load 7 days before the target day, which is the day whose electric load demand we aim to predict. Thus, our task is formulated, as illustrated in the equation, as learning the percentage change of the load with respect to the load 1 week before. Therefore, during training, the network learns a percentage change by minimizing a loss function. Usually, the smooth L1 loss, as illustrated, is used in anchor-based methods, while various losses can also be employed. During the test phase, the predictions are converted back to the original load space so as to be compared with the ground truth targets of actual load and evaluate the performance of the proposed method using the mean absolute percentage error MAPE. Moving on to the experimental evaluation. In this paper, we deal with electric load demand forecasting on Greek energy market. Thus, historical load data provided by the Greek Public Power Corporation are used. Weather information like temperature obtained from Opel Weather is also used. 6 years of data are used and MAPE is used for evaluation. We developed 3 different setups based on the availability of historical load data and the weather information of the target day. So in the typical setup, both all past load information as well as weather information are available. In the partially realistic setup, weather information of the target day is not considered as available, while in the fully realistic setup, apart from this, there is a gap in the historical load data. We first used a simple single-layered MLP and subsequently a 2-layered MLP and a ResNet model. In the typical setup, we have used as input features the load of the previous day, of previous week and previous month, and their corresponding temperature values, as well as the temperature of the target day. Furthermore, we have used 2 binary indicators of weekend and holiday, and an indicator of which day of the week is the target day. In the partially realistic setup, we do not use weather information, while in the fully realistic one, we also do not use the load of previous day. In the first table, we see the evaluation results using the simple MLP with different loss functions for the proposed method against the baseline, which refers to the same model trained with the actual load values. We can observe that the proposed method improves the baseline for all the used losses. Furthermore, we see that marginally better performance is provided by the L2 loss. In the second table, we see the experimental results for the three setups. We can see that the proposed method is superior against the baseline in all the considered setups. And finally, in the third table, we see the experimental results using the optimal loss on the typical setup for the two-layered MLP and the ResNet, where the proposed method provides better performance in terms of MAPE. As it was initially mentioned, this work was conducted in the context of Malena project. Malena is financially supported by European and Greek national funds. Thank you.